Welcome everyone to section 3. In our previous section, we discussed acquiring data from various sources such as spreadsheets and databases. In this section, we're going to cover NumPy and Panda libraries to transform and organize our data so that we can perform some basic data analytics and descriptive statistics. First, we're going to discuss NumPy arrays using one-dimensional data. Now, NumPy is a numerical library that allows us to do a lot of calculations fast and efficiently. Now, some of you might be wondering, why would we use NumPy instead of Python? Well, NumPy arrays are more compact and more efficient to do computationally intensive tasks, such as big data and data analytics. While it might not seem that big of a deal to use a NumPy array or a Python list, it becomes a much bigger issue once we have, say, 1 million lines of data. Alright, so let's initialize some NumPy arrays. First, we'll need to import the NumPy library like so. In a lot of cases, we want to, by default, start off with an array full of zeros. In this case, we'll write something like the following. As you can see, we created a NumPy array that is full of zeros and is of length 3. You can see another example if we want, say, a length of 5. And just like with zeros, there are many cases where you want to write an array full of ones. Okay, well, let's create a NumPy array, but this time let's put some initial values that we'd like to have. Let's go through another example. Okay, well, let's go through an example in this case where we already have a Python list, but we want to convert it into a NumPy array to make it more efficient. So NumPy has this feature called aRange, which allows us to specify a number that allows us to create an array that has a certain length. We could also specify a start point and how much, if any, between steps that we'd like to have. Here, I'll go through a couple examples and you'll get a feel of what I'm talking about. So if we want to create an array that starts at 0 but is of length 10, we could write something like the following. Now, what if we want to create an array that is starting at 2 but ends at 7? Well, in this case, we could write two numbers that will initialize where our start endpoints will be. In this case, I want to start at 2 and end at 7, but to be inclusive, I need to write the number afterwards, which is 8. So what if, in case I want to write an array that starts at 2, ends at, say, 10, I want to skip every other number. In this case, I could add in a third parameter, which skips the intermediate values. So let's just say I want to write a range of values that start from 2 and end at 10. In this case, I'll need to specify 3 values. The start point, which is 2, the end point, which say I want 10, and then I want to skip values. So let's just say I want to skip every other value. So in this case, it would be the value 2. And I'll show you exactly how this turns out. So as we could see, the value started at 2, and we're skipping every other value. So from 2, it goes up to 4, and then to 6, 8, and 10. And we specified that the endpoint was 12, but it's non-inclusive. So it's just going to include the value 10. But if we added something like 14 or something higher, or something like that, then it would have included 12. Now, give a range that gives us a definitive start and end point. That's not always guaranteed that we'll get the exact size or the length of the array that we would like. This is especially important to note when you're dealing with fractions or float point numbers. So if you have a fixed length that you would like to use, then I would highly recommend using linspace. So let's walk through some examples of how you might use this feature. So in this case, we create an array that starts at 50, ends at 100, but we split it into 7 distinct pieces. Let's write another example. In this case, we'll start from 1 to 20, and then we'll split by 3. Now that we know how to create our own arrays, let's discuss ways to access and modify them. So let's first discuss indexing. Indexing is pretty straightforward in the sense that it still works the same way as a Python list. So let's walk through some couple examples. So here's the array 1, just to refresh our memory. And then let's see how we could access the first element. Here's another example of how to access the third element. So let's just use what we know about the indexing syntax to iterate through our values. Now, if we want to properly iterate through a Numpy array, we need to use the nd-iter. Here, I'll show you exactly how this is done. Now keep in mind that the reason why we use NumPy is to make our operations faster by vectorizing them and thereby reducing overhead. So if you can find ways to do so, try to minimize using the standard Python list and, when necessary, iterations. So let's move on through slicing. Say we wanted the second, third, and fourth elements, array 1. We could do something like the following. Here's another example where we take the third and fifth element and just go through one more example. And just like with Python, we could also append two lists or arrays together like so. So in this case, I'm just appending to array 1 the one element list of 1. Here's another example where I'm going to add the list 1, 2, and 3 that contains the elements 1, 2, and 3. And here's a third example where I append arrays 1 and 2. Now let's go through the split method, so in case we want to partition or separate a list into distinct components. So what's going to happen is I'm going to split array 1 where it's going to have values 0, 1, 2, 3, and 4 on one array, and then 5, 6, 7, 8, 9 in the other. So I'm splitting into two equal parts. Now, if I don't want to just split a NumPy list into 2 or 3 distinct components, I could also give it indices where I would like it to partition by. So in this case, I'm splitting index 3. So I have an array of 0, 1, and 2. Then I'm splitting it again at index 5. So the second array contains the fourth and fifth elements. Then I have element 5, and then I have an array that takes all the rest of the values. Now, if I want to get some useful information from our array, I could call something like array1.size instead of calling the length. I could also get its shape. This could be useful when we have more than a single dimension. Now let's get into the heart of why we're using NumPy. So as I mentioned before, NumPy is primarily for vectorized math, and it has some cool additional functionalities. Now let's just walk through how we could do scalar and vectorized addition and subtraction, and along with some other common mathematical properties. So in our first case, let's again refresh ourselves by printing out our first array. And this time, we're going to add to each element the value 5. So if we compare our first array to the output of the second operation, we could see that each element has been added by 5. We could also write an example such as where we're adding 2 arrays. Here, I'll walk through creating 2 new arrays that we'll add together. So in this case, I'm using numpy's .add functionality, but it basically works the same way as what we've been doing earlier. Now let's go through subtraction. In this case, I'm subtracting 10 by every element, so almost all values are going to be negative. And likewise, we could use the np.subtract to our 2 arrays. And in case you're wondering, we could also write x1 minus x2. Alright, so let's move on to scalar and vectorized multiplications. In this case, let's just say that we want to multiply array 3 by the value 3. In this case, I just put the star and the value 3. And we multiply each element by 3. Now let's multiply 2 vectors together. So just for reminders, let's print out x1 and x2. So let's see what happens when we multiply 2 of our vectors. So in this case, each element is going to be paired with its corresponding element. So 1 is going to be multiplied by 10, 2 is going to be multiplied by 20, and 3 is going to be multiplied by 30. And then of course we could also write it x1 times x2. So let's now divide our array 2 by the value 20. And let's divide 2 of our vectors that we had previous from each other. Now let's walk through exponentials and roots. In this case, let's just put to the power of 2. So instead of a multiplication, I could differentiate by putting 2 stars instead of 1. I could also write np.power and then provide the 2 arrays that I had earlier. Now, if we want to do square roots, all we need to do is just do a fraction of our powers. Here's an example of us using the np.power function with our 2 arrays. And in case you're wondering, we could also do dot multiplication. So let's just say that we want to do the dot multiplication of 1, 2, 3, and 2, 4, and 6. So for those of you that are not familiar with dot multiplication, basically you do element-wise multiplications of each corresponding element from array 1 and 2, and then all of those values are summed up together. So in this case, 1 is multiplied by 2, 2 is multiplied by 4, and 3 is multiplied by 6, which gets you 18. So 18 plus 8 plus 2 equals 28. One of the nice features about NumPy is that we have access to a lot of internal stats functions. So let's walk through a couple of them. So if we want to find the minimum and maximum values, and by extension the range, we could use the min and max functions. So let's go through a couple of them. Now that we calculated our minimum value, let's calculate the array 1's max value. Now to calculate the range, all we need to do is just subtract the max value from the min value. Now here's how I calculate the min and max values for array 2. To calculate the total or the sum of our arrays, we could use the sum function. Here's the sum of arrays 2 and 3. So let's move on to NumPy's unique function. So unique will allow us to provide an array, and it will return all of the unique elements that are in that array. In this case, I'm just going to go ahead and write a unique list. Now, as you can see in the array that we created, it has several elements that are shown, but when we're returning the array, we're actually just showing just one time for each unique element. Now, NumPy doesn't have a mode function, but we could use the unique method to actually give us the frequency of every element that it sees. So now that I have that the unique function has the return counts set to true, it actually provides us two results. The first is all of the unique elements within the original array, and the second is the number of appearances or frequency each element shown. So in this case, the counts match directly with the unique element. So 0 is shown one time, 1 is shown 3 times, 2, 2, 3, 2, the element 5, 2, and then 6 and 8 are both shown once respectively. So while this might not give us the mode, we can actually see that just finding the highest value in this frequency count, we know that the mode is going to be 1 because it appears the most often. And just like with min and max, we could also find the mean and median by calling their respective functions. Let's find the median of another array that we'll just create. Now let's calculate some variance and standard deviation. So this wraps up one-dimensional NumPy arrays. While NumPy arrays allow us to perform quick numerical calculations, we need a way to store and organize table data.